In this section, we're going to look at the actual reactions between acids and bases. Now, before we do that, we got to kind of identify or at least define a couple new terms. We're not learning a new way to write reactions, just a couple pieces within an acid base. So the term that we're going to talk about is what's called conjugate acid or conjugate base. It's real simple. The conjugate piece is the structure that's left over after a hydrogen or a hydroxide has left that acid or base. And that's it. Just that leftover piece. So if we're talking about an acid, when an acid were to dissociate, the hydrogen's going to break off, and there's going to be that leftover piece. Now that leftover piece, we're going to call it a conjugate base. The reason we call it a base is because that leftover piece is going to act like an acid, or is going to act like a base. Simple example, HCl. If we break apart, dissociate hydrochloric acid, we're going to get the hydrogen ion separated from the chloride ion. That chloride ion acts like a base. Now, why does it act like a base? Because the chloride ion can accept a proton to become a new chemical, HCl. This is the definition of a Bronsted-Lowry base. Why? Because it can accept, it is possible for it to accept a hydrogen ion or a proton. It's not going to produce an OH, it's not going to produce an H+, it's not going to produce a proton, but it can accept a proton to make HCl. Now if we take a base, if it dissolves or dissociates, the hydroxide ion is going to separate from that leftover piece. That leftover piece has acid-like properties, and we're going to call it a conjugate acid. A straightforward example would be sodium hydroxide. Sodium hydroxide, if it dissociates, it's going to dissociate into hydroxide ions and sodium ions. Now, sodium ion can act like an acid. You look at it, you say, wait a second, how can it act like an acid? It doesn't have H's, so it can't be an acid. It doesn't have hydroxide, so it can't be a base. No, but what it does have are protons. So what does that mean? It can be a proton donor. Also, it can be an electron acceptor. That's a Bronsted-Lowry acid, and that's a Lewis acid by definition back in section 2. Okay? So again, just our point here is if we understand the concept of conjugate is that leftover piece, and it has the opposite properties because there's things that could happen to that leftover piece that fits one of the definitions. Okay. All right, so conjugate acids, conjugate base. So if we look here, if we have HF, which is what we call a weak acid, if that weak acid were to break apart, it would break apart into hydrogen ions and fluorine ions. That fluoride ion is a conjugate base. It's the leftover piece of a weak acid, therefore it has a base properties. If I write it another way, we could also say, well, what if I take HF and react it with water? It's the same thing as doing up here, I just didn't write plus water. Well, there's F minus, that's still a conjugate base. The other piece in this example is H3O. Well, what happens here, if we look at it, is water in this example actually acts like a base. Why? Because it accepts a hydrogen, right? It goes from H2O to H3O. Wait a second, I thought water was neutral. Can be neutral. It also can act like an acid or base. So water in this example is a base. So the leftover piece of water, the conjugate of water in this example is an acid. Down here's another example. This is acetic acid, the acid in vinegar. If we look at this example here, that hydrogen at the end breaks off and bonds with water. The leftover structure of that acetic acid is that. And it's a conjugate base. The leftover structure of Water is H3O plus, and that is a conjugate acid. The only way you can do this is if you see the reactions, and that's our point here is given a reaction, we should be able to identify what's going to happen and what are we going to be left with. Here's two other examples. We just look at these two here, and again, we're given the reaction. I want on the left-hand side, and I'll pause this. I want you to, on the left-hand side, identify what's the acid and base. Okay, so on the left-hand side, both of these reactions, what's the acid, what's the base, and on the right-hand side, identify what's the conjugate acid and the conjugate base for both of these. Okay. All right, so I'll pause this, give you a minute, and just think about the definitions. Which one of these two is the acid base? Which one of these two is the acid base? Over here, which one's the conjugate acid base? Which one of those two is the conjugate acid base? Okay, so if we look at these on the first reaction, the HCO3 is a base. The water acts like an acid. How do we know that, or why do we know that? Because if we watch here, what happens to the HCO3? It becomes H2CO3. So even though there's a hydrogen in there, we think it's an acid, what happened to it? It actually accepted another hydrogen, another proton. So this chemical is a base. Its leftover piece now has acid-like properties. Water, even though we think of neutral, if we see what happens to it, water lost a hydrogen. It lost a proton. It was a proton donor, hydrogen donor. Therefore, it, by definition, it is an acid. Its leftover piece is clearly a base. We know that from hydroxide ions. Down here, HNO3, it's an acid. Why? Because we can see it has lost that hydrogen. That leftover piece is a base. The sulfate ion is a base ion. And again, we know that because we see what happens in the reaction. It accepts a hydrogen. Now, is this always going to be the case? No, it depends upon what it's reacting with. If you remember the last couple examples, water was acting like a base. Here it acts like an acid. And that's our goal, is just given a situation, be able to identify what is there. All right. We talked a lot about strong and weak acids and things like that. So here's a little reminder. The stronger the acid or base, okay, if it's a strong acid, then its conjugate is weaker. So again, we can say it. If the acid or base is strong, its conjugate is weak. If the acid or base is weak, its conjugate is strong. The last thing here, we want to remind, what are all these strong acids and bases by definition? This is something we talked about in section 1, but wanted to remind you again of what they are. What is the significance of these, saying strong or weak, the conjugate's the opposite, so on and so forth? Well, there's a table in the book and it talks about relative acid-base strength. So in relative acid-base strength, what we're going to see is we have acids listed here. Now, they have a whole bunch of them. We haven't talked about all of them, but you can see here, here's hydrochloric acid, here's sulfuric acid, here's nitric acid. Increasing acid strength. So the ones at the top are strong acids. Now, if you look directly across, here's the chloride ion. Here's its conjugate. Well, what's its conjugate? This is a strong acid, but its conjugate is a very weak base. So if we look here, increasing base strength. So if this is a strong acid, its opposite piece, its leftover piece, its conjugate piece, is going to be a weak base. Now if we go down all the way to the bottom, Hydroxide, we haven't talked about all these, but hydroxide is a very strong base. Well, its conjugate is water, and water is a very weak acid. You do not have to memorize this chart, but you do need to understand how they're in, what the relationship is between them. If something is strong, its leftover piece will be weak. If something is weak, its leftover piece will be strong. And we've got that, that partnership that works there. You know? We've been talking a lot about water. Okay, so we'll kind of look at this here. Water actually can be an acid or a base. Even though we talk about it being neutral, it depends upon what it's paired with. And this will be important when we get into chapter 15. But there's just two examples where in the first example, water is acting like an acid. And in the second example, water is acting like a base. It's acting like an acid here because it's donating a hydrogen to the NH3. Here it's like a base because it's accepting a hydrogen from the acetic acid or that weak acid. So it's really both. So you can copy those down, and again, we briefly talked about. Last thing I'll say about this, well, what is that then? Well, it's what we call amphoteric. An amphoteric chemical is one that can act like an acid and act like a base. This reaction right here is a very, very, very important one that we will use in chapter 15. It looks very simple, but it's extremely important because this leads us to the pH scale. Okay. So this is the first part of 14, or the last section. I got one little thing we want to talk about, reaction writing. It'll be short and sweet. Okay. So first part there is section 3 and 14.